Okay, great, thanks. Um, Hello, everyone. Welcome to today's GIST Lunch seminar. I'm happy to have today Chris Cullimore, who's going to be presenting about evidence that abundant aerosols promote tropical cyclone formation. So Chris is joining us from CUNY, where he's currently a postdoc fellow as part of the NOAA CESSRST program. I'm sure there's a better way to say that acronym. He received his PhD from UCLA, where he looked at the role that aerosols play in hurricane formation. And he's currently also in the middle of a 6-month residency at GFDL. So without further ado, Chris, I'll pass this off to you, but just one quick comment before I do that. With these seminars, we have a chat feature where people can write in the chat if they have a question. I can read that, or they can ask it themselves. You don't have to monitor it, but I will be prompting you throughout in case somebody does have a question.
Okay, sounds good. Normally when you think of a postdoc, you think of someone in their late 20s. As you can probably tell from my gray hair, I'm a little older than that. I got a master's degree in atmospheric science back in 1989, but I didn't get my PhD in atmospheric science until 3 years ago. So I think I might be the oldest postdoc in the world. And I think I'm proud of that. Not sure, but I think I'm proud of that. Before I get going here, I want to thank Lazarus Oriopoulos and Jimmy Booth and Clara Orbe for making this all possible. I'm really excited to be able to speak to you guys today. So I'm going to get right to it. As you can see, I'm going to be talking about aerosols and TC tropical cyclone formation. I don't know how many people listening are who specialize in tropical cyclones, so I'm just going to do some very quick background here. Tropical storms are just weak hurricanes, and tropical depressions are really weak hurricanes, and together we call them tropical cyclones, or TCs for short. Some quick background on how TCs form. This is a, Clara, can you see my cursor? Can you see my cursor moving?
Yes, I can see that.
Okay. This is a hurricane about ready to slam into Florida. A few days before that, it was over here, and it was much smaller. And the day before that, it was even smaller. And the day before that, it was just an innocent cluster of clouds. The point is, all TCs start as much smaller clusters of convective clouds. The National Hurricane Center monitors the location of cloud clusters that show promise of developing into TCs. And they predict which ones will go on to develop into TCs. And the predictions are pretty good, but they could still use some improvement. And that would be very beneficial because a harmless cluster of clouds can spin up into a tropical storm strength TC in less than 6 hours. And when that happens near the coast or near islands or near ships, that does not give people much time to prepare. So people who live near the coast or on islands, or people who work in the Navy or on cruise liners, would appreciate better forecasts of TC formation. How do forecasters predict formation? We know TCs come from clusters, but convective cloud clusters are a dime a dozen. You see them all throughout the tropics every day of the year. What set this cloud cluster apart from all the others? And the answer is the environment. There are at least 5 environmental quantities that need to be right in order for a cluster to evolve into a TC. The big 5, I call. The sea surface temperatures need to be warm. The mid-level humidity needs to be high. The lapse rates need to be right. The vertical wind shear needs to be weak. And the low-level vorticity needs to be high. You'll notice the first 4 of these are important for strong convection. And that's what it's all about, the convection. A cloud cluster needs to have strong, vigorous convection in order for it to develop into a TC. Now, in recent years, several studies have shown that there's another environmental quantity that may affect TC formation. These studies have shown that abundant aerosols inhibit TC formation. Now, the thing is, most of these studies took kind of a bulk approach. They averaged aerosol content for an entire storm basin for an entire storm season, and they compared it to TC activity for the entire storm basin and the entire storm season. I said, well, let's really dig in there and look at the aerosols in the immediate vicinity of the clusters just for the lifetime of the clusters. So I took a more targeted approach at asking the same question. Do aerosol concentrations influence TC formation? And the first approach I took to investigate this was I averaged aerosol content around cloud clusters that developed into TCs. And I also averaged aerosol content around clusters that looked like they were going to become TCs, but fizzled out instead. And then I compared the two averages. If aerosols are more abundant for the non-developers, that would be evidence that aerosols do indeed inhibit TC formation, as the prior studies found. But if developers have more aerosols, that would indicate that abundant aerosols promote TC formation. So what data did I use? For the cloud clusters, I looked at clusters in the Atlantic over a 15-year span, 2005 to 2019. And I only examined clusters that were monitored by the National Hurricane Center. I left it up to the pros to determine which clusters at least had a chance of developing into a TC. There were 434 such clusters, 220 developed into TCs, 214 did not develop into TCs. And all the data I'm going to show you for developers are pre-Genesis. The data for the developers starts on the day that the National Hurricane Center started to monitor the cluster up until the day before TC formation took place. For the aerosol concentration, I examined aerosol optical depth, also known as AOD, as measured by the MODIS satellite instrument. AOD is primarily a measure of how many aerosols are present in a column extending throughout the entire atmosphere. But as we all know, the vast majority of aerosols are in the troposphere, which is where TCs form. Other data I'm going to show you, relative humidity and cloud top pressure come from the AIRS satellite instrument. And just about all of the other data I'm going to show you come from the AERO5 reanalyses. So what did I find? This is a plot of AOD, aerosol optical depth, and it's a difference plot. It's the mean AOD in and near developers minus the mean AOD in and near non-developers. We've got north-south here on the y-axis and east-west here on the x-axis. Sun glint interferes with the measurement of AOD, so there are fewer measurements in the eastern third of the plot here. So you want to pay less attention to what's going on in the eastern portion of the plot. The white circle represents a typical size of a developer or a non-developer. You might be surprised to see measurements of AOD inside the circle because many of you probably know that AOD cannot be measured where it's cloudy, but the center of a cluster is defined by the center of its low-level circulation. And the clouds are often asymmetric about that center. So you might get situations where the center of the circulation is right here, and there are clouds in this half of the area, but not this half. It's clear over here. Or maybe there's just a few gaps in the clouds. And if you composite data from enough clusters, you can get a reliable mean inside this area here, and that is what I did. The pink, red, and white indicate higher values of AOD for developers, and we see the plot is dominated by those colors, indicating more aerosols for developers, not fewer aerosols as the prior studies would indicate, more aerosols for developers. And I want to call your attention to the very large differences up here to the northwest. Now, aerosols out here on the perimeter are not likely to affect the cloud clusters. So when it came time to get quantitative, I just analyzed AOD inside this white dashed box here. This box is meant to represent the area containing aerosols that can be drawn into the cluster with the low level inflow. When I average AOD inside that box, I get a value of 0.255 for the developers and just 0.200 for the non-developers. In other words, developer AOD is 28% higher. That's a big difference. And that difference is significant at the 99.9% level using the Mann-Whitney U-test. And in fact, all of the data I'm going to show you in this presentation is significant at the 99.9% level, unless I state otherwise. Where do the aerosols come from? Well, the SAL, the Saharan air layer, is a likely candidate. I think most of you probably know the Saharan air layer is a layer of warm, dry, dusty air at mid and upper levels that forms over the Sahara and then migrates westward over the Atlantic. This is a plot from an earlier study by Wang, and it shows AOD from MODIS, averaged for the boreal summer for these 5 years. And it just shows you where the SAL typically is located over the Atlantic. And it shows where the aerosols from the SAL typically wind up. Now, the thing is, this area to the south of the SAL is what they call the main development region, and a lot of TCs form here. So you can imagine that a cluster that forms here can draw in air from the SAL and aerosols from the SAL with its low-level inflow. And that appears to be what happened here. You'll notice these large aerosol values for these differences indicating large aerosol values for the developers. These appear to be spiraling into the cluster cyclonically from the north. Now, if the SAL is the source of the higher aerosol content we see near the developers, then it stands to reason that developers that form near the SAL would have even higher aerosol concentrations. So what I did is I made the same plot, but just for clusters east of 70 degrees west. If you'll notice here, the SAL kind of peters out around 60 or 70 degrees west. So made the same AOD difference plot, developers minus non-developers, but now it's just clusters east of 70 degrees west. And you'll notice the very, very large differences to the northwest. That's the main difference between the plots. Here's the old plot. This is for the whole basin. This is for east of 70. And the main difference is that these differences to the northwest get much, much larger. And they extend into the white box here. When I average values in that white box, they jump from 0.255 for the whole basin up to 0.278 for clusters just east, for developers just east of 70 degrees west. The numbers for the non-developers don't change very much, which indicates that the non-developers are staying away from the SAL, which I think is very telling. Inside the white box, the developer AOD is 36% higher than non-developer AOD, very large. And when I compare the AOD up here in the northwest, when I average values for this blob up here to the northwest, the developer AOD is 56% higher than the non-developer AOD. Very, very large differences. So the primary point so far is that aerosols are more abundant near developers. But we can't infer that aerosols influence TC formation from that because I haven't taken these guys into account, the big five. I haven't accounted for their effect. Maybe the developers were over warmer sea surface temperatures than the non-developers. Maybe the developers had higher mid-level humidity. Maybe all 5 of these quantities were more favorable for formation for the developers than for the non-developers. And maybe the higher aerosol content was just along for the ride. Maybe the higher aerosol content we saw in their developers was just coincidental. So I need to isolate the influence of the aerosols from the influence of the other 5 quantities. So what I did is I essentially removed the influence of the big 5 by creating a subset of the developers and a subset of the non-developers. And in order to be included in these subsets, the clusters had to have similar environments in regard to the other 5 quantities. And I hear some noises there. I think maybe someone is not muted. So please, everyone, please check to make sure that you are muted, because we don't want to distract people. Okay, so these subsets here with similar environments. So, for example, take SSTs, for example. Here's a cluster, and what I did is I averaged SSTs inside this ring here with an inner radius of 450 kilometers from storm center and an outer radius of 650 kilometers from storm center. And I averaged SSTs in this ring here for each cluster, and for the cluster to be included in the subset, the mean value of the SSTs had to fall within a relatively small medium range window. So I only included clusters with mediocre values of SSTs in the environment. And then I repeated that process for the rest of the for the other 5, the other quantities that comprise the big 5. And the result of these similar environment subsets was smaller subsets, but still plenty of cases. 72 cases in the developer subset, 71 cases in the non-developer subset. Now, here are the mean values of those 5 quantities for the developer subset and the non-developer subset. And more importantly, here in the third column, we have the value of the significance test for the difference between these 2 means here. Now, customarily, a difference between 2 means is not considered statistically significant unless the significance test reaches the 95% level. And you can see that these are Mann-Whitney U-test values, by the way. And you can see that all of these values are all well below the 95% level. And that's good. That was the desired result. The goal was to create 2 subsets with clusters that had similar environments, clusters that had insignificant differences in terms of these 5 quantities. So we got good subsets here, and these subsets put the developers and non-developers on a level playing field with regard to the big 5. So now when we go back and make that AOD difference plot using the subsets, we get it's much more meaningful. It tells us much more about the influence of aerosols on formation. So that's what I have here. This is the AOD difference plot, developers minus non-developers, for the similar environment subsets. And we can see, once again, the plot is still dominated by the colors indicating a higher AOD for higher aerosol content for developers. And it's not the best color scheme here. These negative values here make it look like these are big negative values for these are big negative values, but they're negative, but the magnitudes are not that big. The magnitudes only get up to about 0.09, negative 0.09. Whereas over here in the Northwest, these are some of the largest values on the plot. These get up to 0.20, positive 0.20 in the positive range here. Now, when I average AOD inside the white box, I find that developer AOD is 11% higher than non-developer AOD. That's a decent difference. It's not as big as what we saw before. That difference is only significant at the 94% level, so close to the 95% cutoff for statistical significance, but not there. So kind of not there, but close. So we're kind of iffy results here for the values inside the white box. But when I average AOD inside this black box here, representing AOD up here to the north, in the region to the northwest, I find that developer AOD is 47% higher than non-developer AOD. And that is a significant result, statistically significant result. So when the other 5 quantities are out of the picture, aerosol concentrations are still significantly higher for developers, implying that abundant aerosols favor TC formation. The big 5 can't account for the fact that the developers developed and the non-developers didn't in these subsets, because they were roughly the same for both subsets, at least in the mean. But so maybe the aerosols made the difference. Maybe the abundant aerosols near the developers pushed them over the edge and allowed them to develop into TCs. Now, some quick quality control issues here. I don't have time to get into this, but relative humidity can bias AOD measurements. This is something I really looked into thoroughly. I spent a lot of time on this, and I'm very sure that the AOD developer minus non-developer AOD differences we saw were not biased by developer minus non-developer relative humidity differences. So no biasing there from RH, relative humidity. And also, I'm confident that the differences are due to more aerosols for developers as opposed to larger aerosols for developers. And I determined that by looking at the fine mode AOD product from Modis. Okay, so I'm going to shift gears here. I'm going to quickly take a sip of water here, excuse me. Okay, my throat needed that. So I didn't want to rely just on the difference plots to investigate the association between aerosols and TC formation. So I also used logistic regression to investigate this. If you're not familiar with logistic regression, it's similar to linear regression, but the dependent variable is binary. In this case, TC formation or no TC formation, developer or non-developer. And what happens in the logistic regression process, the binary dependent variable is turned into a probability. So in this case, the independent variables predict the probability of formation. And what I love about this is I didn't have to throw out any data. Did not have to throw out any data. I did not have to use the subsets. We want the influence of SSDs and wind shear and the rest of the big 5 in this analysis. So I included all of the developers and non-developers. I did restrict it to those east of 70 degrees west. The independent variables are the big 5 and aerosols. The data I used to represent the big 5 are the same data I discussed before when I told you how I built the subsets. It's the average of the quantities in those fat rings around, big fat rings around the clusters. And the data I used to represent the aerosols are the average AOD values inside the black box. So here's a schematic of where the data came from. AOD was averaged in here. The rest of the quantities were averaged in these rings here. Now, logistic regression is another way to determine if there's a correlation between, a true correlation between aerosols and TC formation. And at the same time, it will give us an indication of how important aerosols are compared to the other relevant factors. How important aerosols are relative to the other factors. So here are the results. In this column here, we have the Wald chi-square value. This tells us the impact on the predictions from each quality. tells us the predictive power of each quantity. We can see here that AOD had the biggest value. The bigger the value, the bigger the impact. So the AOD appears to be a major player here, but really by far the biggest value here. The value in this column is a significance test. It tells us how sure we are that this value represents a true correlation between aerosols and TC formation. And that significance test the result is 99.99%. So we're extremely sure that the predictive power here is a true predictive signal. Now, I should tell you that a friend of mine ran these regression results. I made it easy for him. I made 6 different files, each one containing data for each of these quantities. And so he could just feed it into his regression routine. And but I didn't tell him which file corresponded to which parameter, which quantity. So this was a blind test here, in case you think I massaged the data or anything. But I should tell you that the aerosols had an advantage in that I focused on the region containing the biggest differences here. If I had done the same thing for the other quantities, like for example, maybe a certain quantity had bigger differences in this one portion of the ring compared to another, and if I had just included means for that region, I might have been able to get bigger values here for these other quantities, but that would not change what we get here for AOD, at least not in any substantial way. We would still get a big impact here and high significance. Now, the one number I'm not showing you here is a number that shows you the sign of the correlation between these quantities and TC formation. And for AOD, it's positive, so indicating more AOD, higher chances of, or more aerosols, higher chances of TC formation. So that checks out, that's what's expected. And between that and these values here, we know that aerosols have a very strong correlation with TC formation. And of course, the difference plots show that too. But as we all know, correlation does not mean causation. I need to show that there's a physical mechanism linking the aerosol content to TC formation. And there's at least 2 possible physical mechanisms linking the two. There's an indirect mechanism which involves the suppression of convection near the cluster. And there's a direct mechanism which involves the invigoration of convection within the cluster. Let's talk about the indirect mechanism first. Prior studies have shown that when there are abundant aerosols present, they can reflect sunlight back out to space, leaving less sunlight to be absorbed by the ocean. So when you have lots of aerosols, you tend to have cooler SSTs. Many of the aerosols that including some of the aerosols that reflect solar radiation, can also absorb solar radiation, resulting in increased air temperature. And since many aerosols in the Atlantic, especially those associated with the SAL, are at mid-levels, those warmer temperatures increase stability. The cooler SSTs and the increased stability inhibit convection. So let's say we have a region here with lots of aerosols, and we have a cloud cluster nearby. This cluster is going to draw in mass and moisture with its low-level inflow. If there was lots of convection here, they would do the same thing. They would draw in air with their low-level inflow, and they would compete for mass and moisture with this cloud cluster. But since the abundant aerosols inhibit TCs because of cooler SSTs and more stability, there's less convection here, and this cloud cluster has less competition. And it can draw in all the mass and moisture at once, which enables it to develop into a TC. So the question is, this region here has lots of aerosols for developers. Does this region have less convection or shallower convection? And the answer is no, it does not. This is another difference plot here, but now it's cloud top pressure. developers minus non-developers. And the purple, blue, and teal indicate lower pressures for developers and therefore taller clouds for developers. And we see up here to the northwest, the developers had taller clouds, more convection, stronger convection, or both. So no, the indirect mechanism does not appear. I think that's all I want to say there. Yeah, the indirect mechanism does not appear to be taking place. Now, I put a caveat there because there are better measures of where convection is than cloud top pressure, and I'm going to look at those. That's on the list of things to do. But cloud top pressure is pretty darn good. I've worked with this data before, and it's a pretty good indication of what the deep convection is. So I'm not optimistic I'm going to get any different results. At this point, it's not looking good for the indirect mechanism. What about the direct mechanism? Oh yeah, now you'll remember here that inside this box here, we did see developer AOD was higher, just 11%, but up here to the northwest, we saw much higher differences here. And that may be, a lot more aerosols for developers, and that may be all it takes for this direct mechanism. Abundant aerosols can invigorate convection through a 6-step process. And I think most people attending the seminar here are familiar with this process. If you're not, so I'm not going to walk you through it here, but if you're not familiar with this process, abundant aerosols can invigorate convection in a method, you can think of it like cloud seeding. It's not the same, but you can think of it that way. And it's just for convective clouds, and it's in the beginning you get less rain and weaker clouds, but in the end of the cloud's lifetime, you wind up with stronger convection, more rain, stronger convection, stronger updrafts, more intense convection. And of course, as we've talked about that, if that convection is inside a cluster, that increases the odds that the cluster will develop into a TC. So the question is, does this process take place? So the first step is we need more aerosols. Well, I've shown you that. I showed you this a minute ago. This is just a close-up image here, the AOD difference plot. And you can see here to the north and west, outside and inside the cluster here, we see these big differences here, indicating more aerosols for developers. And mostly throughout, but especially in the north and west. So yes, we check that off the list here. That part of the process is in place. The next step is that leads to more and less smaller cloud droplets. Do we see smaller droplets? The answer is yes. This is a difference plot of cloud particle radius. And again, developers minus non-developers. And once again, this is a close-up zoomed in image here. Cloud particle radius is an arbitrary measure of cloud particle size. For our purposes, cloud particle volume is more important. When I convert these radii to volume, I find that the average developer cloud particle volume inside the circle is 11% higher than the non-developer cloud particle volume. And that's a decent difference, but over here to the north and west, we see that the cloud particle radii and less volume are much smaller. The radii are much smaller here for developers. And that's what we're interested here, because that's where the extra large values of AOD are for developers. Now, these two plots should not match perfectly here. AOD can only be measured where it's clear, and cloud particle radius, of course, can only be measured where it's cloudy. So you're just looking to see if the two plots are similar in the same general vicinity, and that is what we see here. Yes.
Chris, there's a clarification question. Kostas asks, these are at the cloud top only, right?
No. Cloud particle radius is a measure of throughout, well, I don't know if it's throughout, but a good portion of the convective clouds. It's not just at the top. We get data from well into the cloud. I am just scanning my memory banks here. I'm pretty sure they can't get all the way down to the bottom, but it's probably about halfway down anyway. We get values of cloud particle radius.
Also, sorry, just before you go on, we have another question from Allegra. Allegra, do you want to ask that question?
Sure. So when you're saying developers, does that mean like during the full lifetime of an event? So something could develop 2 weeks later into a hurricane, or does that mean it's developing into a hurricane within a certain time frame or distance from this region that you're where its formation is?
This is the data here includes data for cloud clusters, and when you talk about developers, from the time the National Hurricane Center started monitoring it right up until the day before formation. So this is right up to.
So you could have a disorganized area of convection milling about off of West Africa for 10 days, not going anywhere, that ends up drifting out of the aerosol area and developing once it hits warmer sea surface temperatures with less air, all the other formation things, and it would count as a developer. I mean, yeah, it's just a little bit, I find it a little bit funny that all the things that we traditionally associate with hurricane development, like the statistical tests, don't flag any of those things as being important for developing into a hurricane, yet we know that those things are important.
Well, first of all, the developers, it's not going to be a disorganized one. The National Hurricane Center doesn't start monitoring them until they look like they're very close, pretty close to.
They monitor tropical depressions. That's when they start monitoring.
Yeah.
Not organized. They're just depressions.
Well, they're we're talking about an MCS, which has a fair amount of organization to it. And no, as I said, this is, we're still looking at the.
In which case, like the logistic regression, like on or off, like why that? If you want to do like modes, like, oh, it's a little bit developing, a lot developing, why on off?
Little bit developing. I don't know if there's a way.
Why developers? Why is it a binary system instead of like a? There's a whole intensity spectrum of tropical cyclones, right?
After they form, but in the cloud cluster phase, I don't think they have any sort of measure of intensity. It's just a cluster that they deem has some potential of developing into a TC. And there's no the range of the winds at the low levels are very small. They're talking about maybe 15 and up to 35 meters knots, I'm saying. So there's not a big range there. But to go to you asked something before. You said that well, maybe this cluster can be start near Africa and then 10 days later hit some warmer SSDs. This is all subset data here I'm showing you here. This is we took that out of the picture. The developers and non-developers here all have similar SSTs. So that information is out of the picture for these plots here that I'm showing you. Okay, I kept them in for the logistic regression, but for these plots, we've made sure that the developers and non-developers have similar environments. And also, I should tell you that the typical, the average length of period that these clusters were monitored was about 2.5 days. 10 days. There are some that lasted about 10 days. That's rare, but it's usually just like 2.5 days worth of data here for both the developers and the non-developers. So it's pretty much right before the developers develop. Does that make you feel better?
I don't think my feelings factor in here, but
I mean, I didn't mean it that way. I mean, have I allayed some of your concerns?
It just seems like, the things that we traditionally associate with hurricane or tropical cyclone development and intensification, your analysis pretty much rules those things out as being important at all, which to me, it means like if you just take a step back, forget about the aerosols for a moment and say, can your analysis flag the things that we think are important for cyclogenesis as being important. So just put aerosols to the side and say, is my technique able to flag the things that are important?
So you're saying you're going back to the regression here, where I show the other ones are not so important, like SSTs? Is that what made you think that? Are you saying that these values here are lower?
It's strange that the things that we consider to be important for formation or a development of tropical cyclones aren't important in this analysis. I mean, aerosols aside, like put the aerosols aside for a moment, and just all these 5 things. If you just think, can you find, when you do your renewed analysis, do you flag anything as being important for cyclogenesis besides AOD?
Well, all of these are, except for wind shear, I'll talk about in a minute. These values, because they're smaller than AOD, don't mean that they're not important. You know, these are still showing positive, values here. These are nothing to sneeze at here.
It's not this figure. It's the other one that says developers versus non-developers and shows the significance is lacking for everything but AOD. It just seems strange.
Well, I'm not sure.
I'm sorry. You're probably about 2 or 3 slides from your finish. So why don't we discuss at the end?
Yeah, I think there's a misunderstanding of that. I'm not saying the other ones are not important. I don't. If I showed some data that made you think that, then I must have not described it very well. I do not believe the other 5 factors are unimportant, and I don't think there's anything I've showed that indicates that. Anything I've showed you that indicates that. So we'll have to come back to that. All of the others 5 are important. I'm just showing that aerosols also seem to be important. Okay, the big 5 are still the big 5. So I was talking about we've got the excuse me, the more aerosols here. Do we see the smaller droplets? And these 2, yes, and if you look at the general vicinity here to the north and west, we have higher AOD, higher aerosol content for the developers, and that is where we see the much smaller cloud particles for the developers. So we check that off the list. Yes, we do see this in the direct mechanism here, where we invigorate convection with abundant aerosols. We do see smaller droplets there. Does that lead to taller clouds? The answer is no. Again, no. I've showed you this before. This is cloud top pressure. It's just a close-up, zoomed-in image now. And these differences here inside the circle are not significant. And in fact, they show slightly smaller, shorter clouds for developers. And even up here to the north and west, these are not large magnitude. These differences are not large in magnitude here. So no, we do not see taller clouds there. I made it a dashed line instead of a solid line because, once again, there are better measures of where the deep convection is, and I will look at those. And again, I don't expect anything different because cloud top pressure is pretty darn good. So it doesn't look good for the direct mechanism either. So we have a mystery here. There's a strong correlation between high aerosol content and increased chances of TC formation, but no evidence of any physical mechanism tying them together. This is a perfect situation for a model experiment. One of the beautiful things about models is they often reveal processes that are taking place that we never would have dreamed of. And so it's GFDL to the rescue. One of the great things about my postdoc is that I get to spend 6 months at another NOAA lab, and I chose GFDL. And as many of you know, there are many modelers here and many models. And Ming Zhao and a group of other scientists here and I are using a high-resolution version of the AM4 to investigate this issue. And we're just in the setup stage now. But here very soon, in the next month or 2, we'll make some model runs, and hopefully those model experiments will provide some insight as to what may be linking the aerosols to the TCs. And if we do discover a physical mechanism, if they do unveil a physical mechanism, that would be good, because that would mean the big five are really the big six. And the forecasters at the National Hurricane Center would appreciate having an extra tool to use to predict formation. And people who live near the coast and on islands and on ships would very much appreciate having even better forecasts of formation. So I'm going to skip through some stuff here. Just one last issue. My results appear to conflict with those from the prior studies. The prior studies showed abundant aerosols inhibit TC formation, and I showed that abundant aerosols seem to promote TC formation. But I do not believe my results conflict with those from the previous studies. It seems, how is that possible? Well, if you step back and realize that the different approach I took makes a big difference. The previous studies compared seasonal means and basin-wide means of aerosols and TC activity. I took, as I mentioned before, I took a more targeted approach, and I just looked at aerosols right around the clusters just for their lifetime. So that's just the big picture. Now, digging in here a little more, the previous studies showed that abundant aerosols inhibit TC formation through the same process I described before when I was talking about the indirect mechanism that could possibly link aerosols and TCs. The abundant aerosols induce cooler SSTs and more stability. And therefore you get fewer clouds or weaker or shorter clouds, and therefore you get fewer cloud clusters, and therefore you get fewer TCs. You can't have a TC without a cluster, and you can't have a cluster without an individual cloud. So the previous study showed that aerosols inhibit TC formation by nipping it in the bud. The action takes place at the very beginning here with the individual clouds, and the aerosols kill the TCs before they even get going. The thing is, aerosol-laden air masses rarely, or I would say never, cover the entire tropical Atlantic. For example, here's a dust plume coming off of the Sahara over the Atlantic. Lots of aerosols here, but to the south, relatively pristine air, relatively aerosol-free air. And that opens the door for a cloud cluster to form. And this cluster could benefit from these aerosols here. I don't know how, and I don't know why, but I got a lot of correlations saying that this cluster would benefit from these aerosols being nearby. Now, so you've got aerosols killing convection and therefore TCs here and helping TC formation here. The thing is, the clusters, I would think, would have to be in a relatively narrow band to the south of this air mass in order to benefit from the aerosols, whereas the air mass itself covers a big, wide area here. So I think the negative effect is, more area is experiencing the negative effect, and a smaller area is experiencing the positive effect. And I think overall, the negative impact wins, okay? So I think on balance over a season, over the whole basin, the negative impact wins, and you get fewer TCs. I think the prior studies are right. I think I just said all that there. Yeah, the negative effect dominates. So to kind of sum it up, for the seasonal forecaster, an above average year of aerosols in the Atlantic means there's going to be smaller chances of TC formation. For the operational day-to-day forecaster, who spots a disturbance, a cluster, close to an air mass with lots of aerosols, that probably means that cluster has a better chance of developing into a TC. So everybody's happy. The prior studies are right, and hopefully I've found something here too, but as I said, we still need those physical mechanism to tie everything together. So my conclusions. Aerosol concentrations are higher in the environment of cloud clusters that develop into TCs compared to the concentrations in the environmental clusters that do not develop. And those differences still show up when we take the other 5 relevant environmental quantities out of the picture, which indicates that aerosols do play a role in TC formation. Logistic regression results back that up and indicate that aerosols are a major player in TC formation. But unfortunately, I was not able to find any evidence of a physical mechanism linking aerosols to TC formation. And I also found that the SAO appears to provide many of the aerosols near the developers. And finally, I don't believe there's any conflict between my study and those findings before, which found that aerosols inhibit TC formation. I think they dovetail very nicely. Now, maybe my favorite slide of the whole talk here, because I love thinking about the future possibilities here. Right. First of all, like I said, I need to look at those other measures of deep convection. Cloud top pressure is very good, but not the best. So I want to look at those to see, further investigate those 2 mechanisms that may link aerosols to TCs. I need to investigate the vertical structure of the aerosols near developers and the types of aerosols, liquid or solid, chemical composition. Those may explain why some of the mystery we see going on here. And of course, I need to complete those model experiments. I'm very eager to find out what those reveal about the physical mechanism linking TCs and aerosols. And no matter what I get with those models, no matter what results we get, I think it would be very beneficial to use another model with better microphysics to investigate this issue. The AM4 and the C192 AM4, which is what we're using, they don't have very strong microphysics. So I'd like to use another model with a better microphysics, maybe a mesoscale model, to investigate this issue. Because I said invigoration and microphysics may play a big role. That would be very interesting. And that leads into a shameless plug I'm going to make here. My postdoc ends in the middle of January, so and I'll be a free agent at that point. So if any of you, if my work here fits in with any work that you're doing or any projects that you have going, let me know. Or if you're writing a proposal for a new project and you think my work would fit in nicely, please contact me. I'm open for hire as of mid-January. And if you just want to contact me, I'm open for any kind of collaboration, or if you have any questions, feel free to contact me. There's my email at the top. This is the final slide. And I just want to thank all the people who helped me here. You see their names there, who worked with me on this, and then thank the good organizations that helped fund this study. So that's it. Thank you for listening.
Great, thank you, Chris. That was a very interesting talk. So we had 2 questions that came up. One was a little bit earlier from Kostas. Kostas, would you like to ask that?
Yeah, of course. Thanks for a very nice presentation. I was a little bit concerned that you are using AOD as the single metric for the presence of aerosols. And the reason I am concerned about that is because AOD needs to be in cloud-free conditions, and whatever interactions are happening between aerosols and the potential tropical cyclone formation is in areas where clouds are probably very abundant. And then the people that do the retrievals are doing their best to retrieve aerosols as close to the cloud as possible in an accurate way. But that means frequently that the local relative humidity is high, and that affects the AOD, and this might be skewing your data. So I was wondering how many data points do you have in general throughout your analysis in related with AOD compared to the whole scene, and how close this is to the clouds that might affect, local effects might affect the AOD itself?
Well, the first thing to worry about there, first thing to consider is that if you're worried about biasing from the relative humidity, as I said, I went over it very quickly, but I looked into that very thoroughly. And the relative humidity, I'm looking for that plot. The relative humidity near the developers was not nearly was not that much more than the non-developers, or at least not larger enough to cause the AOD differences that we saw. It's not even close. And I looked at that backwards and forwards. If you have let's say mid-range, if you start with relative humidity at 70%, which is kind of what we see at mid-levels near these clusters, you need to get an increase of about 20% RH to see a difference, to see an impact on AOD. And we were getting more like 5-6% increases, not close to the 20%. And I even did a study where I only looked at developers that had lower relative humidity in their environments than non-developers. I made 2 other subsets, okay? And I looked at relatively dry developers and relatively moist non-developers. And all the developers in the subset had lower relative humidity at mid-levels than the non-developers in this subset. And I got the same results. So the other thing to consider here is, we're looking, if you look at the scale here, this goes up to 2,000 kilometers away here. So a lot of this, the AOD here is a pretty good distance from the cluster, and it can still be eventually drawn in with the low-level inflow. So that's another thing to worry about. Where you talked about how right near the cluster, the AOD, the relative humidity can be high, but away, if distant, especially out here to the northwest, who knows what the relative humidity can be up there? It can be pretty, a lot lower. Okay. And I think you had one other question about how many data points I had.
Yeah, so the cloud masking that AOD retrievals are using might be very intense in your scenes just because it's a cloudy area. So I was wondering whether seeing this exact picture, for example, when you are at 1,000 kilometers away, and you draw a box of 1,000 kilometers wide that goes close to the center of this circle that you have there. If you do an analysis there, probably you are getting only the AOD data of the top left corner of the box rather than a representative area of AODs. So maybe you're just seeing some aerosols further away that will have less impact of what they closer aerosols that are below clouds that you cannot see. I don't know if that makes sense to you.
No, I'm confused. When I make a mean here for this box, it's for the whole area here. And the same when I showed you a black box here, it's for that whole area.
Right, but the AOD is not uniformly distributed in that area because part of that area will be cloudy. And you will not have data for AOD for part of that area.
Yes, I will. If there's AOD here, if it shows I have AOD for that area. It may not have as many values. Some areas might be more frequently cloud-free, so I might have more from one portion compared to another. So that's true. I don't know if that's makes a big difference, though.
That was exactly my question. Whether you have enough cloud-free data points that are spread throughout your box instead of just concatenated in one corner, and then that might affect your analysis. That was my question. Yeah.
Oh, okay. Yeah, I haven't done anything on number of observations at this point versus this point versus that point. So, and I haven't. It's been a long time since I've looked at the significance at each point here. But that's worth looking into. That's a good point.
Thank you.
Great, thanks, Kostas. So we also have 2 questions from Ron Miller. Ron, would you like to ask them?
Yeah, sure. Thanks, Chris. This is really interesting analysis. I'm wondering if the correlation you're finding is actually could reflect the fact that TCs are actually bringing dust into the region. So, for example, you can imagine that the developing cases are rotating faster than the non-rotating cases because they're spinning up. As you mentioned, you've got this strong gradient of dust with the Saharan air layer to the northwest. And so one possible interpretation of the correlation is that, the dust may not be doing anything. It's just being drawn in, by the fact that some of these storms are spinning up. And, the place you would expect to see the dust first, given that you've got a cyclonic circulation, is to the northwest. So I just wanted to know if you've thought about that.
No, I haven't. That's an interesting take on it. And the National Hurricane Center does estimate the low-level wind speeds with the and so I could do that. I could average the wind speeds for developers and non-developers, and maybe I'll find something that shows that the developers had higher winds. I've never heard anyone say that that's the case, but maybe no one's ever looked at it. At this early stage, the winds are not real strong. They kind of range, like I said, between 15 knots and 35 knots. But the 35 knots are kind of rare. It's usually around 20 or 25. That's what it seems like the vast majority of times, either 20 or 25. But, maybe in the mean, maybe the developers have significantly higher winds. I'm glad you said that. I'm going to look into that.
Thanks.
Great. Thanks. So we have one comment. Max Kelly writes, low level vorticity was one of the big five. So let's see. At this point, I can't see kind of too many other questions, and I can't see any raised hands. And we're already about 6 minutes over. So with that, Chris, I think that we're going to close this for now. I want to thank you again for giving this interesting talk. And I want to remind everyone that this has been recorded, and it should be posted to the GIST site within about a week or so. So I want to thank everyone again, and have a nice
Clara, there was the woman who asked a question earlier in my talk. She suggested maybe we talk more at the end. Maybe we can stay on here. She and I can stay on, and I can further answer her questions. Does that sound okay?
Sure. I mean, so Jay, can you do that? Because I actually I have to run. I've got a 2 o'clock. I'm running late for myself. Yeah. Sorry.
Well,
another time.
Yeah, feel free to email me, and maybe we can talk on the phone sometime.
Sure. Okay. Super. Thank you very much.
Yeah. Great. Thanks again, everyone.
Thank you all.